Hello students, welcome to Basic Electronics and Communication Engineering. The subject code is 21ELN14. We have 5 modules in this subject. The module 1 consists of electronic circuits. The prescribed textbook for this module is Electronic Circuits, Fundamentals and Applications by Mike Tooley. Here the DOI number is also given. So if you click on this, here is the DOI number. So in this DOI number, you can get the ebook of the Electronic Circuits, Fundamentals and Applications. This is the first video of this subject and module 1. This module consists of power supplies, amplifiers, operational amplifiers and oscillators. As the days goes on, we will be discussing amplifiers, operational amplifiers and oscillators. So in the initial 2-3 videos, we will discuss only power supplies. This is the syllabus of Basic Electronics and Communication Engineering. The course code is 21ELN14. Weekly we will have 4 hours of classes. Total hours required to complete this subject is 40 hours. The total credits are 3. 50 marks is for CIE and 50 marks for ACE. So total marks is 100. The examination is for 3 hours. So what are the objectives of this course? Remember, the course means this subject. The first objective is to prepare the students with fundamental knowledge or overview in the field of electronics and communication. The second objective is to equip the students with a basic foundation in electronic engineering fundamentals required for comprehending the operation and application of electronic circuits, logic design, embedded systems and communication systems. And to inculcate in first year engineering students an ethical and professional attitude by providing an academic environment inclusive of effective communication, teamwork, ability to relate engineering issues to broader social context and lifelong learning needed for a successful professional career. And you can go through the teach and learning process. There are few general instructions. You can download this syllabus from video.ac.in. Go through neatly. The module 1 consists of the power supplies. Power supplies consists of block diagram, rectifiers, reservoir and smoothing filters, full wave rectifiers, biphase rectifier circuits, bridge rectifier circuits, voltage regulators, output resistance and voltage regulation. Lastly, the voltage multipliers. The other topics we will deal that in later videos. Module 2 logic circuits, module 3 embedded systems, module 4 analog and digital communication, module 5 cellular wireless networks. So totally 5 modules of the electronics and communication engineering. So this will give you an overview of the electronics and communication engineering. So after studying all these 5 modules, what are the outcomes, the course outcomes? So at the end of the course, you will be able to describe the concepts of electronic circuits encompassing power supplies, amplifiers and oscillators. Present the basics of digital logic engineering including data representation, circuits and the microcontroller system with associated sensors and actuators. And you will be able to discuss the characteristics and technological advances of embedded systems. And you will be able to relate to the fundamentals of communication engineering spanning from the frequency spectrum to the various circuits involved including antennas. And the last course outcome is you will be able to explain the different modes of communications from wired to wireless and the computing involved. But out of 50 marks of CIE, the 10 marks are for conducting few experiments. So there are totally 5 experiments and 6 simulation experiments. Let us directly move on to the first topic, the DC power supply. Here the diagram shows the block diagram of the DC power supply. DC power supply, this power supply will supply the DC. Here for this power supply, the input is always high voltage AC. The government will supply 230 volts 50 Hertz AC here. So we need a DC power supply at the output. So what we do here is, first we use a step down transformer to convert the high voltage alternating current to low voltage alternating current. We will step it down according to the requirement of 12 volts or 16 volts. Then this AC is applied as the input to the rectifier. A rectifier is a circuit which converts AC to pulsated DC. So at the output of the rectifier you will get unsmoothed DC. You will not get a perfect DC. Perfect DC is a straight line. So here the output of a rectifier is a pulsated DC. Later we will see the waveforms. So this unsmoothed DC is applied to a reservoir or a smoothing filter. Usually the capacitor is used as a reservoir filter or smoothing filter. So this will smooth the DC. That means the ripple will be reduced to a very small value. But we need a constant regulated DC. Regulated means even if the input voltage is varied or the output load current is varied, you should get the constant DC voltage. So that will be taken care by the voltage regulator. Voltage regulator regulates the smooth DC and supplies a constant DC or a regulated DC. Remember, regulation means if the input voltage changes or the output current changes, the output should not change. So this is the block diagram of a DC power supply. So let us go through the theory, what is written here. Since the mains input is at a relatively high voltage, that means 230 volts, a step down transformer of appropriate turns ratio is used to convert this to a low voltage. So according to our requirement, we will select the turns ratio. The AC output from the transformer secondary A is then rectified using a conventional silicon rectifier diodes to produce an unsmoothed, popularly known as pulsating DC output. This is then smoothed and filtered before being applied to a circuit which will regulate or stabilize the output voltage so that it remains relatively constant in spite of variations in the load current and incoming mains voltage. Here this is just a block diagram. We will not know what is this step down transformer, how a rectifier looks, what is this filter, what is this regulator. But here in this diagram, it will show the principal components of those blocks. So high voltage high voltage AC is applied to a step down transformer. Here if you see, number of primary and number of secondary winding looks same, but actually if it is a step down transformer, the number of windings in the secondary should be less than the primary. So while reading the symbol of a step down transformer, be careful. So this low voltage AC is applied to a rectifier. Here given is a bridge rectifier. Then the output of the bridge rectifier is unsmoothed AC. You will get the pulsated DC, something like this. Then it will be smoothed using a capacitor filter. So you will get the output voltage like this, almost DC. Then this is applied to a regulator circuit, whether it is a transistor regulator or zener voltage regulator. You can use any one, no issue, or you can use a fixed IC voltage regulator, for example 7805, 7812. So you will get a regulated DC output. The iron core step down transformer feeds a rectifier arrangement. The output of the rectifier is then applied to a high value reservoir capacitor. This capacitor stores a considerable amount of charge and is being constantly topped up by the rectifier arrangement. The capacitor also helps to smooth out the voltage pulses produced by the rectifier. You can see here it will be smoothed out. Finally, stabilizing circuit. often based on a series transistor regulator or a Zener voltage regulator. So let us see a practical DC power supply diagram. This is how it looks. Here we apply the AC input 230 volts. Here is the step down transformer, step down transformer. Here is a bridge rectifier which converts AC to pulsated DC, and that unsmooth DC will be smoothed by this reservoir capacitor. Then here the DC output will be taken out. So here are some fuse to protect the circuit, primary fuse and secondary fuse. Here there is a mains filters to smooth this AC. Here is a heat sink. Definitely the heat will be dissipated here, so it will be absorbed by this heat sink and it dissipates to the ambient. Here there is a regulator which will give you a constant DC output voltage. This is how a DC power supply looks. Then coming to the rectifier circuit, the most popular circuits. There are two types of rectifiers, half wave rectifier and full wave rectifier. Now this diagram is nothing but a half wave rectifier circuit diagram. Here you can see the primary winding where 240 volts is applied. This must be a step down transformer. That means the number of secondary windings must be less than the number of primary windings. 12 volts. So divide 240 volts primary by secondary. You will get 20. So 20 for primary winding of 20, you should have one secondary winding. So if you want 12 volts, when you apply 240 volts to the primary, so you should select a transformer whose turns ratio is 20:1. The secondary of T1 steps down the 240 volts RMS value to 12 volts of RMS. So the turns ratio of T1 will thus be 20:1. Semiconductor diodes are commonly used to convert the alternating current to direct current, in which case they are referred to as rectifiers. Diode symbol is this. So this tells that it allows the currents to flow from anode to cathode only. It is a unidirectional device, so this is taken as advantage to be used in rectifier circuits, where rectifier we convert AC to pulsated DC. So ordinary semiconductor diodes are used. The simple form of rectifier circuit makes use of a single diode, and it operates on only either positive or negative half cycles of the supply. If you connect the semiconductor diode in this fashion, it operates only in the positive half cycle. If you reverse the terminals of this diode, it operates in negative half cycle. So this circuit or this diode operates only in positive half cycle. It converts only the positive half cycles of the input to the pulsated DC, so the name half wave rectifier. Only one half cycle of the input waveform is rectified, so the name half wave rectifier. The mains voltage is 240 volts, that is applied to the primary of a step down transformer. So there is no rule that always you should select 12 volts. Whichever voltage you need, your situation demands, you can go for that. If it is 9 volts, then it becomes 240 by 9, so the turns ratio also will change. As you know, diode conducts only whenever it is forward biased. In forward bias, if it is ideal case, you can replace it by a short circuit. If the diode is reverse biased, it will not be conducting, and you can replace it by open circuit. The diode D1 will only allow the current to flow in the direction from anode to cathode only. In the positive half cycle, let us assume the upper terminal of the secondary winding is positive, the bottom terminal is negative. Earlier there was a diode here which was replaced by a short circuit. Now this is the anode, this is the cathode. Anode is more positive than the cathode. Anode is applied a positive potential and cathode is connected to a negative potential. So the diode is said to be forward biased. If we assume that diode is an ideal diode, then you can replace the diode with a short circuit. Now the current flows in the clockwise direction. Now let us try to calculate or see what will be the output voltage across the load. So this load resistance is in parallel with the secondary winding of the transformer. In between nothing is there because we assumed the diode as an ideal diode. So output voltage will be same as the secondary voltage. Later we will see the waveforms. Now let us move on to the negative half cycle. In the negative half cycle, it is alternating. So this terminal becomes negative, this terminal will become positive. If you remember, the diode was connected in this direction. So anode is at the negative potential, cathode is at the positive potential. So the diode is reverse biased. In reverse bias, you can replace the diode by an open circuit. Now there is an open circuit here. So no current flows. So the output voltage is equal to 0. Let us see how the waveform looks. Suppose this is the secondary winding output voltage. The output voltage will be only this much because only in the positive half cycle you will get the output voltage. In the negative half cycle, the output voltage is 0. It repeats afterwards. Only one half cycle is rectified. So this circuit is called as a half wave rectifier. Since the main supply is at 50 Hz, the pulses of the voltage developed across RL will also be at 50 Hz. The input frequency is 50 Hz. Output voltage frequency is also 50 Hz. Here, this is one cycle. Cycle is a period after which it repeats itself. The output also repeats after this. So the input and output frequency both are at 50 Hz. If you consider the diode as a practical diode, the voltage drop across that diode will be 0.6 volts or 0.7 volts whenever it is forward biased. If you consider the diode as a practical diode. During the negative half cycle, the diode is reverse biased, so output voltage will be 0. Assuming that the secondary T1 provides 12 volts RMS, root mean square value, the peak voltage output from the transformer secondary winding will be given by V peak is equal to root 2 into Vrms. Peak voltage is always is equal to root 2 into Vrms. So if I say 230 volts input or 240 volts inputs, it is the RMS value. If you want to know what will be the peak voltage, then it will be root 2 times the RMS value. So secondary winding peak voltage is given by root 2 into Vrms. So it is around 16.97 volts if 12 volts is the RMS value. The peak voltage applied to D1 is approximately 17 volts. The negative half cycles are blocked by D1 and thus only positive half cycles appear across RL. However, that the actual peak voltage across RL will be 17 volts positive peak being supplied from the secondary and T1 minus 0.7 volts forward threshold voltage dropped by D1. So the total voltage, the peak amplitude at the output will be 16.3. So if you have not understood, here is 240 volts RMS. The secondary is 12 volts RMS. So 12 volts RMS, peak voltage will be 17 volts. This is RMS value. This is peak value, 17 volts. So in forward bias, the output voltage is same as secondary voltage I said. But actually there is a diode here. The drop across this diode whenever it is forward bias is 0.6 volts. So the secondary voltage minus the forward voltage drop across the diode. So it is 17 volts minus 0.6 volts. So it will be 16.3 volts. This is the output voltage across the load. So that is 16.3 volts that is appearing across the RL. Let us go through an example. The mains transformer having a turns ratio of 44:1, 44 primary, 1 secondary, is connected to a 220 volts RMS mains supply. So you can imagine like this, 220 volts RMS, 44:1. So let us go through the problem. If the secondary output is applied to a half wave rectifier, determine the peak voltage that will appear across the load. Calculate the peak voltage V0. So RMS secondary voltage is given by, here secondary voltage we need to find out initially. So primary voltage is 220 volts. Primary voltage is 220 volts divided by the number of turns there, 220 by 44, it is 5 volts. Here is the 5 volts RMS value. Convert this RMS value to the peak value. How to convert? The peak value will be given by √2 times 5 volts. So approximately 7 volts. Here approximately 7 volts is the peak voltage. Now we would like to calculate the peak voltage at the output of the rectifier. As you know, in the forward bias, the diode is forward biased. In the positive half cycle, the diode is forward biased, and assume there is a 0.6 volts drop across the diode whenever it is conducting. So 7 minus 0.6, 7 minus 0.6. So it is around 6.4 volts you will get as a peak voltage across the load resistance. Hope you have understood this example. Now let us move on to the reservoir and smoothing circuits. As you know, this is the input and here secondary reduced voltage. Then at the rectifier you will get the pulsated DC. We want to smooth this, so let us use a capacitor C1 as a reservoir capacitor which will smooth this like this. Capacitor stores the charges whenever the diode is forward biased. In the positive half cycle, this terminal is positive, this terminal is negative, the diode is forward biased, so the capacitor gets charged like this in these polarities. So it will be charged to the peak voltage, In the negative half cycle, upper terminal will be negative, bottom terminal will be positive. The diode is reverse biased. No current flows. You can replace the diode by an open circuit. Now the discharge path for the capacitor is like this. Capacitor starts to discharge through RL. If RL is of very high value, capacitor takes more time to discharge. The charging time constant TC is equal to RC. Charging time. The charging time constant, this R resistance is nothing but the secondary winding resistance, forward resistance of the diode, and a very small connecting wire resistance. And this capacitor value is of C1. So you will get a charging time constant very small, so within no time capacitor gets charged. The discharge time constant is also RC, but diode is reverse biased. So here it becomes RL into C. In the discharge path, the load resistance is there. Usually RL is of very high value. Capacitor also will take a very high value so that it can charge more charges. It can store more charges. So TD is of very high value. So the capacitor takes more time to discharge. Suddenly it cannot discharge. Like this we can smooth the rectifier output. Let us go through the theory. The capacitor C1 has been added to ensure the output voltage remains at or near the peak voltage even when the diode is not conducting. Here the diode was not conducting, still the voltage is almost constant. When the primary voltage is first applied to the T1, the first positive half cycle output from the secondary will charge the capacitor to the peak value. Hence the C1 charges to 16.3 volts. Because C1 and R are in parallel, the voltage across RL will be the same as that of C1. Across RL also you will get 16.3, the peak voltage. So here you can see. This is the secondary voltage waveform. Here this is the voltage across RL when there is no reservoir capacitor. If you connect a capacitor, it will charge. The capacitor gets charged to the peak value and it discharges very slowly because discharge time constant is more. In the one more positive half cycle, once again the capacitor gets charged. Again when the diode is off, it gets discharged. Whenever the diode is on, again the current flows and capacitor gets charged. So it repeats. So this peak to peak, this peak and this peak, the difference between this peak and this value, we call it as a ripple. Ripple is the unwanted component, unwanted AC component in the output of the rectifier circuit. Here in this circuit diagram, two more components are added to smooth and filter out R1 and C2. These are used to filter out the ripple. So half wave rectifier efficiency is very less, ripple factor is more. The diode conducts only in one half cycle, only one half cycle is rectified. So it is very rarely used. So full wave rectifiers are very popular because of their efficiency. Because full wave rectifiers convert both the half cycles, rectifies both the half cycles. There is a lot of improvement in full wave rectifiers over half wave circuits. Efficiency is more. There are two types of full wave rectifiers. One is biphase type and other one is bridge rectifier type. Out of these two, bridge rectifiers are very popular, very widely used. Now the first type of full wave rectifiers, biphase rectifier circuits, popularly known as center tap full wave rectifiers. Biphase. This is the circuit diagram of a biphase rectifier circuit. This is the primary winding. Here the upper half of the secondary winding and bottom half of the secondary winding. The mains voltage, let us assume 240 volts, is applied to the primary of the step down transformer T1, which has two identical secondary windings. So the name biphase. Two identical secondary windings, each providing 12 volts, each providing 12 volts. In the upper half we get 12, here in the bottom half also 12 volts. So what may be the turns ratio of this? 240 by 12, 240 by 12, it is 20:1 for each secondary winding. For each secondary winding. Because in each secondary, upper half of the secondary and bottom half of the secondary, we need 12 volts. So 240 by 12 is 20. Here, for every 20 windings of the primary, we will have one winding at the upper half and bottom half. On positive half cycle, the terminal A will be positive with respect to point B. Similarly, point B will be positive with respect to point C. So here we call it as a ground point, center tap. So the upper terminal will be positive, the bottommost terminal will be negative here. Here is the anode, here is the cathode, here is the anode of D2, cathode of D2. This positive terminal will make the diode D1 forward bias because the anode is at positive potential. The negative potential at the bottommost terminal of the bottom half of the secondary winding will make the anode to be at negative potential. So D2 is off, no current flows. So during a positive half cycle, D1 conducts. Now let us move on to the negative half cycle. In the negative half cycle, point A will be negative, point B will be positive, point B will be negative, point C will be positive. Here this becomes ground point. So upper terminal becomes negative, the bottom terminal will become positive. Now the anode of D1 is at the negative potential. So D1 is not conducting a reverse bias. D2 anode is at the positive potential, so D2 is on or it is conducting. So in one half cycle D1 will be conducting, in the another half cycle D2 will be conducting. So when D1 is conducting, current flows through the load in this direction. When D2 is conducting, the current flows in this direction. So overall through the load always current flows in the same direction. So it is unidirectional. Current through the load is same direction. The polarity will not change. So the waveforms here, this is the primary winding voltage, secondary winding voltage. As the two diodes are conducting and the current flows through the load in the same direction, you are getting the voltage across the RL without the capacitor filter like this. At 12 volts at the secondary, peak is root 2 into 12, so it is 17 volts. This 17 volts, here there is a voltage drop of 0.6 volts. So here you will get 16.4 volts peak voltage. So this is the working of the biphase rectifier during positive half cycle and the negative half cycle. This is during the positive half cycle. This is during the negative half cycle. In the positive half cycle, this terminal is positive, this is negative, this is positive, this is negative. D1 is on, D2 is off. So the current flows in this direction. So you will get the output voltage. This output voltage will be same as the secondary voltage minus the voltage drop across the diode, that is 0.6 volts. In the secondary, in the negative half cycle, this terminal is negative, this terminal is positive, this is negative, this is positive. So D1 is off, reverse bias, D2 is on or forward bias. So the current flows in this direction. So if you observe through the load, the current flows in the same direction. Now connect a reservoir capacitor across the load to smooth the output of the rectifier, that is pulsating DC. Now the output voltage will become 16.3 volts, 16.3 volts. This is the output voltage across the load when there is a reservoir capacitor. Here the capacitor gets charged to the peak value and it discharges, again charges in the one more positive half cycle, discharges, charges, discharges, charges, discharges. 17 volts is the peak voltage. So across the load you won't get 17 but you get 16.3 volts because 0.7 volts will be the drop across the diode. If you observe the frequency of the output voltage across the biphase rectifier, it is 100 Hz if the input frequency is 50 Hz. So how? So this is your time period, 1 by T is frequency, but here this is the time period after which it repeats itself. This is half. 1 by T is frequency. So here the frequency becomes 100 Hz. If the frequency here it is 50 Hz. So that's all in this video. Here we discussed half wave rectifier and biphase rectifiers with smoothing filter and without smoothing filter, and also we went through one example also. In the next video we will discuss the bridge rectifier. Thank you.